Welcome to Cybersecurity Under Pressure. Real attacks, real lessons. Every breach starts with something small. A trusted login, a missed alert, a system no one thought could matter. Here, we follow the incident. How it began, how it moved, what broke under pressure, and what security engineering and business teams should learn before the next one. Because the next attack will not wait for a perfect plan. Now, let's follow the evidence.
Welcome to Cybersecurity Under Pressure. Real attacks, real lessons.
Oh, absolutely.
So imagine a multi-million-dollar robotic arm, right? It's welding the structural chassis of the exact car you drive to work every single day.
Yeah, that's a terrifying thought right out of the gate.
Right. And, the software controlling that arm is perfectly secure. Like, the network is locked down behind industrial firewalls, the firmware is cryptographically signed, it's authenticated, all of that.
All the standard IT checkboxes are ticked.
Exactly. Every single one. Yet the weld holding your car together is fundamentally flawed. It's missing the seam by, I don't know, maybe 3 millimeters, and absolutely no security alarm is ringing anywhere in that factory.
Well, it's Wednesday, which means we finally have some time midweek to step back from the daily firefights and really dig into exactly that kind of nightmare scenario.
Yeah, a much-needed step back.
Right, because we're looking at a pressing issue that has been quietly keeping factory managers, risk officers, and manufacturing engineers awake at night. We're examining this space where the digital world violently, and often silently, collides with physical reality.
And the core of what we are unpacking today in this deep dive is it's a fundamental disconnect in manufacturing and critical infrastructure.
Yeah, the gap between what we think is secure and what actually is.
Exactly. Because for years, if you look at the cybersecurity industry, we have been completely obsessed with software trust. We rely on these deeply complex mechanisms to guarantee safety.
We use secure boot, to ensure the hardware only runs trusted operating systems.
Right. Secure boot, code signing, cryptographic hashes, authenticated binaries. We desperately want to know that the software running on a machine is exactly what the vendor shipped.
But when you step out of the server room and onto a factory floor, physical robotics operate in an entirely different reality.
They really do. As someone who spends a lot of time looking at OT, or operational technology and engineering resilience, I can tell you that a robot controller simply turns programs and parameters into physical motion.
Doesn't have common sense.
No, none at all. It doesn't inherently, know if a weld is a millimeter off because its configuration was subtly changed. It just does what the math tells it to do.
And from the perspective of an attacker, or even just looking at the broader business challenge of defending these environments, that disconnect is the path of least resistance.
Oh, 100%.
Like, why on earth would an advanced threat actor bother spending millions of dollars in research and development to bypass deeply embedded, mathematically authenticated binaries?
It's just not worth the effort.
Right. Why try to break secure boot when you can just alter a simple plaintext configuration file?
Yeah.
The attacker doesn't need to rewrite the robot's operating system. They just need to change the basic math that tells the robot where it is in physical space.
It is exactly like verifying a delivery driver.
Oh, I like this analogy, yeah.
Right, so imagine you hire a highly sensitive courier service. You do a rigorous federal-level background check on the driver. You verify their commercial driver's license.
You're checking all the boxes.
All of them. You make sure the truck they were driving has passed every single mechanical safety inspection, and you even put a tamper-evident, cryptographically verifiable seal on the back doors.
So nobody can mess with the cargo.
Right. You have total, undisputed integrity over the vehicle and the driver. That is our software trust. But then you completely ignore whether that driver actually drove to the correct address.
Right, or if they just tossed it in a ditch.
Exactly. Or if they dropped your package off at a competitor's warehouse, or if they backed that perfectly inspected truck into a brick wall at 60 miles an hour.
Yeah, the integrity of the truck doesn't matter if it's currently on fire in a ditch.
Exactly. We have built this incredibly complex, multi-billion-dollar system for verifying the integrity of the delivery mechanism while completely blinding ourselves to the physical execution of the actual task.
The vehicle is trusted, but the trajectory is compromised. And that brings us to the central question we are going to be wrestling with today.
The big one.
Right. We need to look at this through the lens of recent technical evidence, regulatory shifts, and these just absolutely unforgiving operational realities to ask. What decision is defensible with the available evidence and real operational constraints?
Because the theoretical answers you might read in a white paper almost never survive first contact with a live production line.
They absolutely do not. The constraints on a factory floor are brutal. You can't just reboot a factory like you reboot a laptop.
Technical breakdown.
So to understand what is really happening underneath, let's get into the technical breakdown.
The first thing we really need to separate here is the concept of logical intent versus authorized operation.
Right, which is a huge stumbling block for IT folks.
It is. If you're an IT professional listening to this, you're probably used to a world where if a piece of software is verified and unaltered, its execution is generally considered authorized.
Yeah, if the hash matches, it is good to go.
But in an ICS environment, an industrial control system, an unaltered, completely trusted binary can execute a highly malicious or physically dangerous motion if the parameters feeding into it consist of bad data.
Yeah, because the controller, which is often a programmable logic controller or PLC, is really just a mathematical engine.
That's all it is.
If you feed it poisoned coordinates, it will perfectly and faithfully execute a flawed trajectory. Let's break that down for someone who might not, spend their days programming industrial robotics.
Yeah, let's get into the weeds a bit.
A PLC is essentially a ruggedized industrial computer. It takes inputs from sensors, runs them through a logic program during what's called a scan cycle, and sends outputs to motors or valves.
And those scan cycles are fast.
Incredibly fast. Milliseconds. But the PLC doesn't have eyes. It has math. And this isn't just a theoretical vulnerability discussed in academic circles.
No, this is actively happening.
Right. If we look at the AARE ATT&CK for ICS framework, which catalogs real-world adversary tactics, they have explicitly documented this threat vector.
I think it's under modified parameter.
Yes, exactly. Threat actors do not need to drop custom malware into the real-time operating system of the controller. The framework details how attackers simply modify tool frames, alter speed parameters, and shift positioning values without ever touching the underlying trusted binaries.
And we need to explain the mechanics of how that actually happens physically.
Yeah, how does the math become motion?
So you have a robotic arm. At the end of that arm is the tool, maybe a heavy welding torch, a gripping claw, or, a paint sprayer.
Right.
The robot calculates all of its complex, multi-joint movements based on a single reference point called a tool center point, or TCP.
And this is where the inverse kinematics come in.
Exactly. This TCP is often defined in a simple, unencrypted configuration file. If an attacker gains access to the engineering workstation and subtly alters the X, Y, or Z coordinates of that TCP in the file, let's say by changing a 0.5 to a 0.7, what happens?
The robot's internal inverse kinematics engine just recalibrates everything based on that new lie.
Yes. The robot still thinks it is performing the exact same authorized motion. It reports back to the control room that the manufacturing cycle was completed successfully with 0 errors.
Because according to its math, it was perfect.
Right. But physically, the weld is missing the seam, or the claw is crushing a delicate microchip because it thinks it's 2 millimeters higher than it actually is.
Which is incredibly insidious because the traditional security telemetry that a security operations center relies on is completely silent.
Crickets.
The antivirus didn't go off because there is no virus. The network intrusion detection system saw legitimate, perfectly formatted ICS traffic like Modbus or CIP.
And for context, CIP is the Common Industrial Protocol. It's essentially the language industrial devices use to talk to each other over Ethernet.
Right, so the security tools saw a legitimate engineering workstation sending a legitimate CIP packet to a legitimate controller.
There's no exploit payload to flag.
None. The code signature on the robot's firmware is perfectly valid. This was highlighted brilliantly in the recent Usenix security presentation by Cheng-Tao Yao regarding parameter modification.
That was a fascinating presentation.
It really was. The research demonstrated exactly how altering a trajectory, speed, or physical reference point fundamentally changes the real-world outcome without breaking a single cryptographic trust boundary.
From the attacker's perspective, this is the absolute holy grail.
Yeah, it's the ultimate stealth attack.
In traditional IT, we talk about living off the land, using built-in administrative tools like PowerShell to execute an attack so it blends in.
Right, so you don't have to bring your own malware.
Exactly.
Yeah.
Well, this is living off the land for industrial physics.
Yeah.
You are using the robot's own valid configuration mechanics as the weapon.
And from an engineering perspective, those parameters are the lifeblood of the factory. They are the highly guarded recipes of manufacturing.
Trade secrets, really.
They are. When a new automotive product line is spun up, process engineers spend weeks tweaking those parameters. They adjust the acceleration curve so the arm doesn't vibrate.
They dial in the exact voltage of the welding arc.
Yes, they set the deceleration profiles to get the perfect physical outcome. If someone maliciously recalibrates that, the physical product is ruined.
And potentially, the structural integrity of a passenger vehicle driving down the highway years later is fatally compromised because a weld failed under stress.
Which is terrifying. So the immediate question for anyone defending these systems is, how do we actually detect this?
The detection opportunity here requires a massive shift in how you think about logging.
Yeah, it's not just syslogs anymore.
It is the absolute necessity of recording program versions, manufacturing recipes, tool frames, payload data, and critical physical parameters before production cycle even begins.
You need a known good baseline.
You need identity-stamped and time-stamped monitoring of changes to these specific values. If the tool frame coordinate changes at 3:00 a.m. on a Sunday, and there is no maintenance ticket associated with that specific engineer's identity, that is your primary indicator of compromise.
But capturing that data is just the first step. You have to understand the physical execution and the controller mechanics to do anything useful with it.
Right, having the log doesn't stop the robot.
No, it doesn't. The controller is the brain. It takes the logic and the parameters and translates them into electrical currents that drive the servo motors. The core issue we are facing is whether the observed physical trajectory stays within the authorized behavior envelope.
And this is exactly where the friction starts between engineering teams and cybersecurity teams.
Because my challenge to you on that front is, how do you actually know what authorized looks like in real time?
Right. How do you define that bounding box?
Exactly. How do you measure a millisecond by millisecond physical deviation without completely overwhelming the computational resources of this system?
You really can't, not on a legacy PLC.
No. If you try to mathematically verify every single servo motor movement against a security baseline in real time, parsing millions of data points a second, you are going to bring that legacy controller to its knees.
I completely agree with you on the computational limits, which is why we cannot try to solve this entirely within the digital domain of the controller itself.
We have to look outside the box.
We have to leverage production evidence. And this is where the dynamic fundamentally shifts. We do not necessarily need to invent and deploy brand new, heavily engineered cybersecurity tools to detect this physical drift.
We can use what is already bolted to the factory floor.
You are talking about the physical quality assurance infrastructure.
Exactly. Modern manufacturing lines are absolutely covered in physical sensors that exist entirely to ensure product quality.
They're essentially physical IDS if you use them right.
That's a great way to put it. We have high-speed vision systems that inspect a weld bead the millisecond it's finished, looking for spatter or irregularities. We have laser metrology stations that measure the geometric tolerances of a newly machined part down to the micron.
And torque sensors, right.
Yes, torque sensors on the robotic joints that monitor physical resistance. If the robot pushes too hard, the sensor knows. We have quality gates and downstream physical inspections.
All of these systems provide irrefutable, ground truth evidence of the physical result.
Ground truth, that's the key word. And the beauty of this is that this evidence is entirely independent of the software execution path that ordered the robot to move.
So it bypasses the lie.
Exactly. If the software is lying, the laser metrology system will catch the physical discrepancy.
This is a massive detection opportunity that almost all businesses overlook because of entrenched organizational silos.
Oh, the silos are the worst part.
If you look at most manufacturing companies, the IT and security teams are looking at firewall network logs, while the production and quality teams are looking at defect rates and sensor outputs.
Never the twain shall meet.
Right. Correlating IT and OT configuration changes with physical rejects or quality drift is the missing link.
It seems so obvious when you say it out loud.
It does. If your cybersecurity team sees a configuration parameter change on a Friday night, and the production team sees a 2% spike in weld defects on Monday morning, those two events are currently sitting in different databases, being analyzed by completely different people who do not talk to each other.
And merging those data streams provides a level of physical assurance that no firewall on Earth can offer.
But we have to be extremely careful about how we scale this, which introduces the concept of selective assurance.
Yes, selective assurance.
Assurance depth, meaning how much monitoring, correlation, and telemetry we actually deploy, must scale directly with the physical consequence of the operation and the real-time constraints of the machinery.
Meaning, you don't need this level of deep physical digital correlation for a robotic arm that just moves empty cardboard boxes onto a pallet.
Right, it's overkill.
If that gets hacked and drops a box, the consequence is a minor mess. Someone gets a broom. But you absolutely need it for a robot doing structural spot welds on a high-speed passenger train chassis.
Exactly. And I have to push back strongly on how a lot of the modern security industry wants to implement this.
Okay, let's hear it.
I see vendors constantly pitching tools that sit directly in the middle of the control loop, analyzing industrial traffic, and making real-time automated blocking decisions.
Oh, man. Yeah.
From an engineering and safety perspective, that is a non-starter. Safety functions must remain in independently validated logic.
You cannot mess with the safety PLCs.
You absolutely cannot mix experimental cybersecurity telemetry or active network blocking mechanisms with core safety controllers.
Right, because if a physical safety light curtain is breached because a human walked into the robotic cell, the robot must stop immediately.
Milliseconds matter.
That safety logic is hardwired and mathematically proven to execute in milliseconds. If you put a security appliance in that pathway and it introduces even a tiny delay, or worse, a false positive that interferes with the safety sequence, you are risking human lives.
That is a critical boundary line. The security mechanism can observe, it can alert the operators, it can correlate data, but it absolutely cannot interfere with the deterministic safety loop.
Operational decisions.
With the mechanism clear, let's turn to the operational decisions.
And this is where the theoretical physics of the factory floor meets the brutal, unforgiving reality of legacy controllers.
The brownfield reality.
Yeah. We have to talk about the NIST Guide to Industrial Control System Security, specifically Special Publication 882, Revision 2.
Foundational text.
When you read through that baseline, it becomes painfully obvious how much operational friction is involved when you try to deploy modern IT security controls in these environments.
It is an absolute nightmare, and people outside of OT simply do not understand the sensitivity of legacy manufacturing environments.
They think it's just old Windows machines.
Right. But we are dealing with controllers, PLCs, and ECUs, electronic control units that might be 15 or 20 years old.
Older than some of the engineers working on them.
Honestly, yes. They have processors running at clock speeds that would make a modern smartphone laugh. They have exactly enough RAM to run their specific automation task and nothing more.
So when you add an agent,
when we talk about friction, we aren't just talking about a sluggish application. We are talking about latency and jitter.
let's define that for the audience, because security vendors will often claim their monitoring tools have negligible overhead.
Oh, I hate that phrase.
They will walk into a CISO's office and say, it only takes 5 milliseconds to process the packet and verify the parameter change. You won't even notice it.
Which is exactly the kind of claim that gets manufacturing engineers screaming. Negligible is a highly relative term.
Very relative.
In an enterprise IT environment, if you send an email and it takes an extra 5 milliseconds to route through a cloud spam filter, literally no one notices.
It's invisible.
But in a real-time motion control network, a 5 millisecond jitter, which is the variation in latency, is catastrophic.
Catastrophic.
Think of a real-time industrial network like a conductor leading an orchestra. The conductor's baton has to fall at the exact millisecond the musicians expect it. If the conductor stutters and the baton drops just 5 milliseconds late, the entire symphony crashes. A robotic controller expects a data packet at exactly 10 pointless milliseconds.
Not 10.005.
If it arrives at 10.005 milliseconds because a security tool was inspecting it, the system assumes a critical communication failure has occurred.
It panics.
It throws a hard fault code, and it violently slams the physical brakes on a multi-million-dollar production line to prevent the robots from colliding.
And cost of that is immense.
Every minute that line is down while engineers try to reset the physical servos could cost the business tens of thousands of dollars. You cannot just bolt a security agent onto these legacy ECUs.
And that operational reality isn't just an anecdote. It is actually codified in the International Engineering Standards.
IEC 62443.
Exactly. If we look at IEC 62443, specifically Part 3.3, which covers system security requirements and security levels, it strongly validates exactly what you are saying.
It's written in black and white.
The standard makes it abundantly clear that cybersecurity should not become another process control layer. Its fundamental purpose is to manage access and provide evidence of unauthorized change, not to sit in the middle of the deterministic control loop, making split-second operational decisions.
Exactly. Cybersecurity is an observer and an auditor on the factory floor, not a machine operator.
But there's a massive business challenge here too, revolving around supplier dependencies and regulatory defensibility.
Oh, the lawyers and the warranties.
Right. Let's look at the automotive sector, which has to deal with ISO 73933 and 73934. These are the strict requirements for the development of secure vehicle systems and the audit processes.
Very strict.
If a factory operator decides to aggressively alter the control layer of a robotic cell to insert cybersecurity telemetry, perhaps they want to modify the robotics vendor's proprietary operating system to extract better logs, they're going to run into a brick wall of supplier resistance.
That's immediate.
You immediately void the warranties. The robotics manufacturer will say, you altered our certified homologated configuration. We no longer guarantee the physical safety, the accuracy, or the performance of this machine.
And if that machine is responsible for manufacturing safety-critical components like brakes, steering columns, or chassis, you might also violate national safety regulations.
You're taking on all that liability.
You can't just hack your own factory equipment to secure it without taking on immense legal, financial, and operational liability.
Which brings us to the actual cost of implementation. We have some incredible real-world evidence on this from ABB, a major robotics and automation corporation.
Yeah, their guidelines are fantastic.
They released a document titled Industrial Robot Security, Implementation Guidelines and Operational Constraints. If you are a risk officer wanting to secure a factory, it is one of the most sobering documents you can read.
Because it spells out the harsh reality of the brownfield environment.
Tell us about the difference there.
Well, a greenfield site is a brand new factory built from scratch on an empty field. You can design security architecture from day one. Segmented networks, modern hardware, zero trust principles.
A dream scenario.
Right. But brownfield means retrofitting security into an existing running legacy robotic cell covered in dust and grease running on 20-year-old Ethernet cables.
Where someone lost the network diagram 10 years ago.
Exactly. The ABB evidence details the extreme costs involved in this. It is not just the software license cost of the security tool. It is the cost of the engineering time to manually map a network that has no documentation.
It's the downtime.
It is the cost of the physical downtime required to install and test the instrumentation. It is the immense supplier friction of getting vendor approval for the changes. And it is the ongoing, exhausting operational cost of managing the inevitable false positives that shut down production.
The ABB document essentially says, yes, theoretically you can instrument these older robots, but the latency impact is a real physical threat, and the engineering validation required to prove the security tool won't crash the line is massive.
It's often prohibitive.
It forces a business to ask a very uncomfortable question. Is the return on investment actually there for this specific robotic cell? Does the risk of a parameter modification outweigh the guaranteed cost of a factory shutdown during implementation?
And this brings us right back to the safety boundaries, which is heavily emphasized in the CISA Joint Cybersecurity Advisory on Best Practices for ICS, specifically Advisory AA 23351A.
CISU is very clear on this.
Yes, CISU, the Cybersecurity and Infrastructure Security Agency, reiterates in no uncertain terms that security measures must absolutely not compromise safety or production availability.
So we have to find a consensus here between the security mandate and the engineering reality.
It requires compromise.
I will concede, based on the NIST baselines and the ABB guidelines, that deploying sweeping, plant-wide, real-time telemetry at the controller level simply isn't feasible for most legacy businesses today.
Thank you.
It is too expensive, it introduces too much jitter, and it voids too many vendor warranties. The business case only works if cybersecurity stops trying to invent new proprietary data streams and starts reusing the existing quality gate and metrology data we discussed earlier.
I completely agree with that concession, and that requires a fundamental, painful shift in how the business organizes itself.
Breaking down the silos?
You have to split the ownership of the defense. Production and engineering own the process quality they own to, the lasers, the torque sensors, and the high-speed vision systems.
And what does cybersecurity own?
Cybersecurity owns the evidence of unauthorized change. They own the configuration logs, the identity management, and the access controls. The true defense in depth only happens when those two isolated teams finally start talking to each other and merging their dashboards.
But having a theoretical agreement on an organizational chart is one thing. Knowing how to apply it when everything is on the line, millions of dollars are bleeding out, you have incomplete data, is entirely another.
Pressure test.
That sounds reasonable in principle, but now let's put it under real constraints with the pressure test.
All right, let's set the scene. And I'm going to force a hard decision on you right now.
Okay, bring it on.
Imagine you are the head of engineering and security for a Tier 1 automotive supplier. You produce structural chassis components for major car brands.
High stakes.
It is Wednesday afternoon. Your security operations center has just flagged some anomalous indicators. A configuration file associated with the tool center, the TCP, on 3 of your primary high-speed welding robots has just been modified.
Okay, modifying the TCP on a chassis welder. That is not just a digital anomaly, that is a direct physical threat to the structural geometry of the welds holding a car together.
Exactly. But here is your binding constraint. Your evidence is completely incomplete.
Of course it is.
The legacy logs show a change occurred, but because of the equipment's age, you don't have the exact payload of the change. You know the file was touched, but you don't know if the coordinate moved by 1 millimeter or 10 centimeters.
And the timestamp?
The timestamp doesn't correlate cleanly with a known scheduled maintenance window. Furthermore, there are no standardized industry metrics for what constitutes enough independent evidence in these specific cyber-physical systems. You are operating in a total gray area.
And I have to assume because it's Wednesday afternoon, the line is currently running.
The line is running at full absolute capacity to meet a quota. Every single minute of downtime costs the business tens of thousands of dollars in penalties.
Brutal.
And to make matters significantly worse, a regulatory clock is ticking. You operate under the NIS2 directive in Europe, which mandates rapid reporting of significant cyber incidents. And because you supply the automotive sector, you are strictly bound by UNES R155 and R156.
For the listener who isn't deep in auto regulations, UNES R155 mandates a strict vehicle cybersecurity management system, and it traces the integrity of the vehicle all the way back to the manufacturing floor.
Precisely. If this is a genuine breach that could impact the safety of the final vehicle, and you ship those components, you lose your homologation, your legal right to sell parts.
The business is dead.
You have a strict window to report this, and you cannot wait for a perfectly ideal third-party incident response team to fly in on Monday. We need an immediate decision right now.
Okay, this is the absolute nightmare scenario for an OT defender. We have incomplete telemetry, massive financial pressure from the business to keep producing, and a regulatory guillotine hanging over our heads if we ship a bad part.
So what do you do?
The immediate decision required is that we must isolate the highest consequence motions and parameters, and we have to enable change monitoring against a known good baseline, all without touching or altering the validated safety functions.
Standard IT incident response says you isolate the affected machines, you pull the network cables, you quarantine the subnet, and you image the drives. So what is your first move?
Absolutely not. I will push back on that immediately.
Oh, really?
If we pull the network cables or try to implement an active block on a running legacy robotic line, we will introduce massive jitter. The PLCs will lose synchronization, we will cause a hard, violent fault on the controllers, and we will physically scrap $50,000 worth of high-tensile steel currently sitting in the jigs.
You're worried about the steel?
I'm worried about the physical safety of the cell and the line continuity. We will not isolate. Action 1. We do not block, we passively record.
Passively record. Okay.
We immediately deploy read-only scripts to the engineering workstations, and I am explicitly saying the workstations that interface with the PLCs, not the PLCs themselves, to pull down the current running configuration, the tool data, the frames, the payloads, the recipes, and the critical parameters.
You do what with them?
We take a snapshot of the current state of the math to compare against the last known good baseline backup from yesterday. We just record them. We do not attempt active interference.
I will challenge you on action 1. From the business, regulatory, and evidence side, simply recording the parameters and doing a dig check isn't enough to satisfy the regulators, and it doesn't tell us if the product currently rolling off the line is safe to ship.
Right, because we don't know the physical outcome yet.
Exactly. If the TCP changed, but the robot's physical kinematics absorbed the change safely, the product might still be good. I am immediately getting on the radio with the production floor manager for Action 2.
What's Action 2?
I need to correlate the time window of those suspected digital changes with our existing physical safety checks. We need to look at the data from the quality gates at the end of that specific robotic cell.
Bringing in the metrology.
Yes. Did the high-speed vision systems flag an increase in weld spatter over the last 2 hours? Did the downstream torque sensors on the assembly line report any out-of-tolerance fittings? Did the laser metrology stations show the chassis warping by even half a millimeter? We have to use the physical output to validate the digital suspicion.
That is a solid approach, combining the domains. But Action 3 is non-negotiable from my engineering standpoint. We maintain strict, impenetrable boundaries around the safety functions.
The safety PLCs.
Yes. While you are pulling quality data, I am locking down physical and logical access to the safety PLCs. The incident response team you spin up is not allowed to touch the safety logic.
That's a strong line in the sand.
They are not allowed to run an Nmap scan on those specific subnets. They are not allowed to deploy any agents anywhere near the physical safety light curtains or emergency stop circuits. Those systems remain in independently validated logic.
Because if they crash the safety system...
If the robot goes rogue because the parameters were malicious, the physical safety barriers are our absolute last line of defense to protect human life, and I will not let an aggressive IT network scan take those offline by mistake.
Agreed on the safety boundary. And Action 4. We only escalate new security instrumentation where the consequence justifies it. We are not going to panic and try to instrument the entire factory floor today.
Just the blast radius.
Exactly. We are focusing solely on the 3 welding robots that were flagged. If we determine that the parameter drift is real and the metrology data confirms the welds are out of tolerance, that is our escalation trigger.
That brings us to the critical decision point. What actually triggers you to hit the big red button and cause a line stoppage?
It has to be a combination.
It is not just an anomalous network packet. It is the precise combination of an unauthorized change to a critical parameter explicitly correlated with quality drift or physical evidence of motion outside the authorized baseline.
Because a network anomaly alone isn't enough.
No. If the network log shows a change, but the laser metrology station says the part is structurally perfect and within tolerance, we keep the line running while we investigate the log anomaly offline.
You're not going to stop production for a ghost.
We do not stop a $1 million production run for a digital ghost if the physical reality is sound, but if the log shows a change, A and D, the metrology laser shows a deviation, we hit the emergency stop and we declare a major incident.
But you have to acknowledge the residual risk you are accepting by making this decision.
I do.
By relying on downstream quality checks and periodic parameter snapshots rather than real-time blocking, physical drift may still occur between our observation windows.
Yes, there is a delay.
A compromised robot might manufacture 10 or even 50 defective chassis components before the metrology station catches the error and signals the line to stop.
Right.
Furthermore, the existing physical evidence might not measure the specific compromised variable with enough resolution.
Right, if it's too subtle.
If the attacker subtly altered a welding parameter, like voltage, that affects the long-term metallurgical fatigue life of the weld, but doesn't change its immediate geometric shape, your laser metrology systems won't catch it.
That is the brutal truth of the pressure test, and it is a pill that IT security professionals have a hard time swallowing.
It goes against their instincts.
It does. You have to accept that residual risk to keep the plan running safely. You cannot achieve perfect zero-trust security without destroying production. You are relying on the defense in depth of the physical quality systems to catch what the cyber systems missed, and you accept that some defective product might slip through in the gap.
Key takeaways.
With the trade-offs on the table, let's bring it all together in the key takeaways.
The core convergence point we've reached today, synthesizing all the operational evidence from the NIST baselines, the IEC standards, the ABB engineering guidelines, and the MyRE framework, is that the only defensible decision is to apply selective assurance.
Selective assurance. It's the only way.
We have to apply deep security monitoring only where the physical consequence justifies it, and we must combine IT and OT change monitoring with independent physical production evidence.
If you are a security, risk, or business leader listening to this means you have immediate homework.
Yes, get to work.
You cannot treat every machine on the factory floor as equal. You must rigorously define which physical operations actually require independent evidence based on the worst-case consequence.
The spot welder versus the paint sprayer?
Exactly. A spot weld on a car chassis requires an entirely different level of assurance than a robot spraying paint on a bumper. You also have to establish clear organizational ownership.
Oh, please.
The endless turf wars between IT and OT have to stop. Production, engineering, safety, and cybersecurity must have agreed upon lanes of responsibility before an incident occurs.
Production owns the physical quality.
And cybersecurity owns the evidence of digital change. And finally, you only fund additional telemetry where the residual risk and the consequence explicitly justify the operational overhead and the friction with your suppliers.
And if you are on the technical, operational, or incident response teams in the trenches, your mandate is to monitor parameter and program changes with strict identity and timestamps.
Don't just watch the OS.
Do not just monitor the operating system binaries, you must monitor the math that drives the machine. Furthermore, there is a crucial engineering rule you must follow.
Validate the overhead.
Yes, you must validate the computational and network overhead on the real legacy controller in a test environment before introducing any real-time analysis tools to the production floor.
No testing in prod.
Never, ever assume a vendor's claim of negligible impact applies to a 20-year-old PLC. And most importantly, stop trying to reinvent the wheel.
Use what you have.
Reuse the existing quality, torque, and metrology data as your independent evidence wherever it is technically defensible. The physical factory is already equipped with thousands of sensors telling you if it's under attack. You just have to listen to the right ones.
It really is a paradigm shift. We have to stop looking solely at the software signatures and start looking at the physics of the outcome.
Ultimately, this is why we have to remember that a welding robot can execute trusted software and still make the wrong weld.
Yeah.
The integrity of the code is only half the battle. The physical verification of the action is the true measure of security in OT environments.
Thank you so much for joining us on this Wednesday. It is a complex issue, but unpacking these constraints is how we build real resilience on the factory floor. We will be back with our next deep dive this Friday. Thanks for listening to Cybersecurity Under Pressure. Real attacks, real lessons.
You have been listening to Cybersecurity Under Pressure. Real attacks, real lessons. Real incidents leave real lessons. Stay prepared. Stay critical. And keep following the evidence.